Alright. So, yeah, welcome to CMSC 341. Unfortunately, I have a few announcements because, the first announcement is that Comcast, is really, really terrible. So, last semester they didn't do any of this stuff, but now I think they are rate limiting me and doing all kinds of things to me that prevent lectures from being smooth. So that means I'm going to have to switch internet. I don't know if you guys can hear me or see me right now, or if it's buffering. There are massive buffer issues, all kinds of bad connection problems, etc., etc. Last semester, they didn't do this, but they decided to implement some kind of rate limiting feature in January. I didn't know because we didn't lecture. So, yeah, I'm probably going to get FiOS. I mean, I know that this has nothing to do with Computer Science 341. The only thing I'm going to say is that maybe next lecture will just be pre-recorded. I hate that. I don't want to. But if the issues here are as bad as they seem to me, and they seem pretty bad, then I'm gonna have to do something about it. And so this is priority number one for me right now. I thought it was, so yesterday I was having these connection issues, and I thought to myself, well, maybe it'll resolve itself by tomorrow, and now I suspect that it's just part of Comcast's general plan to get people to switch from Comcast. So, yeah, maybe the next lecture this week will be pre-recorded. Hopefully I can make the switch fast and regular operations. Okay, so that's all I'm going to say about that. I've probably spent way too much time on that already, so I'm just complaining about this because if you see buffering, if you see problems, this is what it is. I can't do anything about it because Comcast has basically destroyed my internet ability, which is, of course, as it turns out right now, my job is through the internet. So they have earned themselves yet another enemy. So I'm going to switch off and do that. Okay, so let's talk about other things than internet connections, but that's just me explaining why. So if you remember that the first lecture for this class was destroyed, that was partially the reason. I thought it had to do with the regular internet outage that day. It didn't. It was completely Comcast. So I've learned my lesson. We will do something. So what are we going to do today? We're going to talk about Project 1. We'll talk a little bit about Project 0 submission, maybe. Someone asked me to go through the submission process a little bit. Yeah, that was an accident. I changed the channel permissions. Okay. So, yeah, I guess we can double check to make sure that that announcement channel, I haven't posted anything there yet. Well, I guess I did post one message, but I just need to make sure that the permissions are set properly. Let's see, make sure that they are. If you are a student, you need to be able to read the message history. Yes, I think no sending, you can react, you can, I guess, emoji, and you can So it should be fine. It should be okay. Okay, and then the other thing that we want to talk about today is stacks, queues, and Deques. So I'm probably going to start with Project Zero submission, and then I'm going to move on to stacks, queues, and Deques, and then finally we'll talk about Project One, mainly because Project One is a queue. So there's that. Okay, so let's talk about Project Zero submission. So let's see, where did I stick Project Zero? Here it is. Okay, so all right, let's see if this loads. You see, it's while I'm streaming, you see how the internet doesn't even load these pages very quickly. It's something is very horribly wrong. Very horribly wrong. Come on. Come on. Oh my god. Okay. So let's look about how to submit. And so there's a what to submit section. Here are the 3 files you have to submit. Let's load up that page. It's going to take forever, I guess. Oh, no, that went. So let's see if... No. Okay. Okay, putty time. All right. It's even slow connecting to GL. I guess I can use this time to change the font size, because I always forget how to do that. Settings, parents, area 20, okay, apply. All right, so that failed. Okay, and now the thing is buffering. So, okay. So let's say that you have your 341 directory. Let's say you're in wherever that is. So let's say that you want to submit Project Zero. So basically you only have to run this command once. And what you're going to do is you're going to do ln, which creates a symbolic link if you do the -s. And then you're going to type in your directory. Or no, I'm sorry, not your directory. You're going to type in the submit directory, which is AFS, mbc.edu. So basically the whole thing here, up to Smurf19, right? So you see how laggy the connection is. I guess I'm still complaining about it because it's taking forever now. There we go. And then I would do like airgate. And then I'm actually in the directory that I want to submit from, so I can actually just do a period here, which means like take it from here. Or actually, no, I'm sorry. You have to do this. So the tilde takes you to the home directory, and then the / will allow you to make a link file name, so then it's CS341 projects, or whatever you want to call it, and hit enter, and then hopefully if we go to home directory, it will, and we do ls, hopefully we'll see CS341 projects. Do we see it? Here it is. And if we go cd, hopefully it works. No such file or directory. So that's probably what I will get because I don't have a student submit directory. But then what you're going to do, hopefully this will actually work for you. And then what you'll do, actually, why don't we just make the link instead of for me. So that's what you have to type in if it's going to go to somewhere. But let's just, I know what to do. Well, okay, this is really slow and really annoying. I am going to close this. Let's see, do I have my VM working? No, I don't. Okay, let's boot up my VM. Let's just do it locally. Okay. Interesting. Okay. So, is there a view channel? Students should be able to view the channel. Yep. Yep. I hear you. As I say, this lecture, unfortunately, may be kind of destroyed. Just like a number of the other ones, this is pretty unacceptable. I mean, it's unbelievable that they're going to do this. I'll tell you what, I'll start recording, and if it's too bad, then maybe I'll have to do something about it. Okay. Alright, well that's having issues, so let's ignore that for now. Okay, well this was a waste of time. Huge waste of time. Okay. And then he's giving you the SCP commands to use to put stuff in your directory. If you're doing your development on the local machine, but I suggest you use WinSCP and not actually do this. Okay. Yeah. Okay. Alright. So, okay, I think I'm going to give up with this submit tutorial because my VM is having issues first time in like a year, and my internet is having issues, so I can't really SSH. I'm not sure. Things are not going well right now. Doesn't seem like anything's really working. I don't know why the VM is screwed up. Let's just reboot it. Let's restart it. Hopefully that'll fix it. Okay, I think I just... Okay. Alright. So, now that all of that has been completely destroyed, let's talk about stacks, queues, and decks. So this is the topic for today. So basically, how do stacks, queues, and decks work? So let's talk about stacks first. So a stack, based on the, what is it? LIFO principle, which is last in, first out. So what does that mean? That if we have a stack element, let's say this is a thing that we put on the stack. Okay, so VM is working a little bit better now. All right, so basically, if you have an element that you want to stick onto a stack, you put it at the base of the stack. So here's the base. And then there's two operations that you really have to be concerned with. So the operations on a stack are push, which means put something onto the top of the stack. And if you draw it downwards, then it's the bottom, but I'm always going to call it the top. And pop is pop something off of the top of the stack. So, for instance, if you have a thing on the stack like this, and then you want to stick another thing on the stack, this would be called a push, right? We push a thing. And then let's do another push, so we can push, say, another, right? And so what you would do is you would say, okay, I'm going to push another thing onto the stack, so this would be another. And then we might push internet or Comcast, right, onto the stack. And so we'll push Comcast onto the stack, this, and now we have Comcast on the stack. So of course what we're going to do, because Comcast is terrible, is the first thing we're going to do is pop off Comcast. So the next thing we're going to do is pop. Now you don't necessarily have to pop Comcast, but the point is whenever you run the pop command, it always pops the top of the stack. So it's always going to take from the top of the stack. And it's going to, wow, this stream must be really laggy if I'm just getting the what's SCP. SCP is if you need to transfer a file from your local machine to the GL server. I know that you had 201 with me, so you probably used it there, right? So anyway, okay, so if we pop off the stack, what happens here, we take this element and we discard it, right? And then if we pop again, let's say we pop one more time. So then what happens is it takes off another and it discards it. Discards go nowhere, right? I'm just putting them over there because just in case I want to copy paste them in a second. So basically what's happened here is we pushed Comcast, then we popped off the top of the stack, we popped off the top of the stack again, and then for instance maybe we'll push something else on. Let's push on Verizon, because that's how it works. So let's push on Verizon, and then we'll do that, and then we'll push on destroy all units. And so destroy all internets will now be okay. So now that's on the stack. So basically, those are the two operations that stacks have. So whenever, basically, what should we do? We should do something like this, and so this goes from the bottom to the top. So that's where, this is where things are pushed onto the stack, and this is where, this is where something is pushed onto the stack, and this is where something is popped off of the stack. So pushing and popping always happen to the first element, right? So push and pop always happen to the first element. So a standard use of stacks, for instance, is like a recursion stack. So for instance, whenever you do recursion, and the reason why it's an example of a stack is, say you have like a factorial function, right? Factorial of n, which is equal to n times factorial of n minus 1, unless n is equal to 1 or 0, in which case return 1. So basically, if this is your factorial function, you know, and I don't care what language you write this in. This is not in any particular language or anything, but this is just in my own little pseudocode language. The point is that the call stack is actually a stack, and that's so. For instance, if you call, say, factorial on 5, what's going to end up happening is the computer actually pushes the return location for factorial of 5 onto the stack, because whenever you call a function, the even if the function is void and doesn't return anything, functions still need to know, or I shouldn't say functions, the computer needs to know where to go once your function ends, right? So when you basically, there's a ret assembly language command in most languages, most assemblies, and that ret is going to, what that ret does is it actually pops off the location off of the stack here, and then it sets the instruction pointer back to there. So what it does is it takes your program back to that location. So for instance here, if we have factorial of 5, which is going to call factorial of 4, so that's going to get pushed onto the stack, and then it's going to call factorial of 3, which calls factorial of 2, etc. 2, and then here we're going to call factorial of 1, which is our current base case. So here is factorial of 1 sitting on top of the stack. So this is what happens when you call factorial of 5. So there's the return location for factorial of 5, the return location for factorial of 4, factorial of 3, factorial of 2, and finally the factorial 1, which tells it where to go back to in factorial 2. So basically here you'll have a memory location to go back to, and so what happens is once factorial 1 finishes running, right, once this finishes, it's going to pop, right? So pop with the result of 1, and then so what we do is we say okay, and then here we're going to pop again with the result of 1 times 2, which is like this, and then we will pop again with the result of 1 times 2 times 3, and then we will pop again with 1 times 2 times 3 times 4, like this. And then the last thing on the call stack is this factorial of 5. So the last pop, now we have an empty stack, and the value returned is correct, right? 1 times 2 times 3 times 4 times 5. So that's an example of a stack. Another example where stacks are used is in language parsing, for instance. So the most common way to basically match parentheses is a stack or recursion, but generally a stack. And the reason why it's pretty useful is because whenever you find this symbol, you push, and then whenever you find this symbol, you pop. And so how do you know if parentheses match? So for instance, what I mean by parentheses matching is something like this. 2 open, 2 closed, or maybe 1 open, 1 closed, then 3 open, 1 closed, 2 open, 1 closed, you know, this one, that one, this one, that one, and finally this and that. So I think this matches if you check it out. What's an example of them not matching on the other hand? An example of them not matching is when you start with an end parenthesis, that doesn't match. Or if you have something like this, where you have more end parentheses than start parentheses, that doesn't work. Or when you start out with like 3 and then you only have 1, basically this is like a dangling expression, right? The compiler generally doesn't know what to do with this. It thinks you want more, and so, you know, to be in here. So these are all examples of where you would use a stack, is in any kind of parenthesis matching problem, any kind of, so the actual hardware on your computer uses a stack to track return locations for recursion. Stacks are kind of useful. So, okay. So let's talk about the implementation of a stack. Okay. Okay. So, yeah, if we talk about the implementation of a stack, there's really 2 primary ways that you can implement stacks. Oh my god, it says no data. That's extremely bad. I really hope that this is not completely screwed up. Probably is. Oh, I forgot to start recording, which I guess is fine. Okay. Alright, so the implementation of a stack basically goes like this. There's really basically the 2 ways you can do it. There's either the array-based approach, and then there's the linked list-based approach. And so both of them are pretty much fine. So if we think about it, how do we implement a stack as an array? So as an array, basically all you have to do is keep track of which index is at the top of the stack. You would probably use, unless you're pretty crazy, you would use 0, right, index 0 as the bottom. And you probably basically use like a vector type approach. So if you ever got to the top of the stack, there's 2 things that happen, right? So if you get to the top of the stack, you have 2 choices. Either you can basically say stack overflow, meaning no more space in this stack. Don't push anymore, please. Right? And so that usually takes the form of an exception. And then the other way to do it is to basically use the vector idea and allocate a new array, copy the old stack array, and then update all the indices. Right, so that's the way to do it with a linked list. Okay, so now how do we do it with a linked list? So with a linked list, there's really 1 or 2 ways to do it. So here's one idea. My first idea is here's the bottom of the linked list, and here's the arrow that goes to the next node. So, excuse me. I always sneeze once per lecture. I don't know why. So, basically, here's a linked list, and here's the bottom of the linked list, also known as the head. And here's the top of the linked list. Which is the tail of the linked list. The only problem is, whenever you're pushing and popping, this would require you to always search to the end. So there's two problems with this. So either you have to track the tail node, right? And if you pop the tail node, you still need to track all the way to the end. So still need to track all the way to the end for pop operations. And even if you keep track of the tail. So for push, if you keep track of the tail, you don't need to go all the way, where you can just jump to the end and insert, right? So that's how you would do a stack this way, right? But I made a choice, right? And my choice was that this one was the head and this one was the tail. And so, as it turns out, this is not always the best way to do it if you just have a single... Now, if you have a doubly linked list and you keep track of the tail, there's no trouble, right? This all goes away with a doubly linked list. But with a singly linked list, this is still a problem. So the way to fix this problem is to actually turn the whole thing around, and you do this. Okay? So now what you see is that whenever you insert, right, you always insert at the head. Oh, I'm sorry, this is not the tail anymore. This is now the head, right? And this is the tail of the linked list. And so basically, whenever you insert, you're inserting at the head, and you're also popping off the head. So you never have to track to the end, right? You never how long this linked list is. You never care about anything other than the head node at one time. So basically, if you try to, whatever you do, you always have something of this form. So this is basically how a linked list works for a stack. And so this is the kind of better solution when you have a singly linked list. If this is a doubly linked list, this is okay. When you have a singly linked list, this is the kind of preferred solution. And the reason why it's the preferred solution is because this one will take n steps to do any pop operation. So this one has a pop operation which is O of n, which is O of the linked list, and this has a pop operation which is O of 1, which is constant time, which means that it's only dependent on the few operations that you have to do. So if you have a stack that's, say, 1,000,000 high, it's going to take you a long time to do pop on linked list, whereas here, it'll only take you a short amount of time. Okay. So, yeah, I guess actually we can implement a, let's implement a stack, because it's not your project. But what am I doing? Here, let's make stack. Okay, so, and let's make a push operation. And a pop operation. And I think that's really it. And then our private data is going to be a linked list. So here we have a linked list in this implementation that we made. So I think we'll just include it included in here. So let's say include linked list h. And now, basically here, all we need to do is have a linked list, link list. Now, of course, this is kind of a dumb way to do it. Most of the time, you implement the linked list inside of the stack class, but here we have a linked list that I've already implemented, so I'm just going to steal it. And so, basically here, what we're going to do is when we push a new thing, we're going to go mLinkedList dot insert. And remember that the data had a thing, and so we insert the new thing, but position 0, right? So this means insert at head always. And then here for pop, oh, we only did remove by value. We only did remove by value. Crap. So dots. Well, we need to get like dot get at position 0, and then we need to like remove. So we need a dot get. But as it turns out, if we had this dot get, then we'd basically be done. Or remove at position. Let's just do a remove at position. So remove at position 0. And that's all you really need to do. Move at position into our linked list class now. Or maybe that's a good homework problem. Yeah, that's a good homework problem. So, okay. Because there's already an insert at position. So I'll have you implement the remove at position. But here's the thing about this stack. Other than the copy constructor, the assignment operator, all that other stuff, this is exactly all you need, right? This is everything you need. So you can either push onto a stack, or you can pop off a stack. Now, of course, if there's nothing at position 0, so if like mLinkedList dot empty, which of course also doesn't exist, then we might want to throw like an std domain error or something and say like, this is a stack underflow. Right? Basically, it just means that there's nothing in the stack, so they should have checked. So maybe bool empty. And of course, I'm getting all these reds because we can implement empty pretty quickly. Right? Empty. All we have to do. I guess phead is not equal to null pointer. So, yep. So that's, I think that would fix at least this here, and then we just have to do the remove at position 0. But as it turns out, this is a stack implementation. It's not a very good one in the sense that you can't display the stack, you can't copy it, you can't do anything else, but it does implement a stack. Right, and we used a linked list. The only thing we had to do was insert at the head, and then here we just, pop by removing the element at the head. And that's it. Okay, so that's enough about stacks. So let's talk about queues, because that's actually your project. So all right, so let's talk about queues. So what's the point of a queue? So a queue follows the FIFO principle, which means first in, first out. And so basically what I mean by that is that a queue is just a line, right? A queue is just a line. Let me see. Here we go. So if you implement a queue, let's copy paste some kind of linked list. to hint that we're going to do it like a linked list. Now, actually, in your project, you're going to do it as a kind of merger between an array and a linked list, but we'll get into that in a little bit. It's actually an interesting project. I haven't implemented it yet, but I probably will implement it in the next few days and tell you anything that comes up as a do. So basically, there's two operations for a queue. There's enqueue, and then there's dequeue. So enqueue means put at the back of the line, and dequeue means remove from the front of the line. And that's it. That's it. Those are the two operations that queues absolutely need to have. All the other ones like empty and copy constructor and all that other stuff, basically everything else is just mechanics, right? So yeah, you can have like an empty, you can have other operations, but if it has enqueue and dequeue, it's a queue. And of course, they have to implement it as a queue. So let's see what a queue does. So let's say that I put some numbers into these boxes. So let's say that I have, say 1, 3, 7, 5. And then let's enqueue. So if we enqueue 13, then what's going to happen is we got to stick 13 here at the front. And that's what we do. So this is enqueuing 13. And then just like with a stack, when you just, instead of enqueuing something like that, you would just do dequeue, right? Because you don't care what the last element is. What happens is that it returns 5 to you. 5 is the returned value. And then the rest of this just gets copied, and basically this gets, the 5 goes away. So when you enqueue a bunch of stuff, it just goes onto the front, and then when you dequeue stuff, you pop it off the back. And so let's think about how to implement a queue as a linked list. So it's not a bad idea how to think about, so as an array, well, let's do a linked list first. As a linked list, so as a linked list first, what you want to think about is which way does it make sense to have the pointers going? Does it make sense? So these arrows, I didn't draw them with any arrow on them. The queue is going this way, but I think it still makes sense to have the linked list go backwards. And let me show you why. So if this is the tail of the linked list, and this is the head of the linked list, then think about how things get enqueued and dequeued, right? So by enqueuing, so when you enqueue, what you do is you need to stick on a new tail. So basically what you're going to do is you're going to keep track of the tail, and you're going to go tail.pnext is equal to the new thing, right? And then what you're and that's it, right? The tail.pnext is new thing, and of course new thing, right? So new thing.pnext is null pointed. And so that's how you're going to implement this thing as a linked list. And so for enqueue at least, right? Enqueue sticks something on the tail of the linked list. So now for dequeue, when we dequeue, what we're going to do is we have to remove from mhead. So we say old head, old is equal to mhead, right? And then what we do is we say mhead equals mhead.pnext. And then finally what we do is we delete the old one, right? And so you might have to save the element, like you return the element that was saved from the deleted node. So you might need to do old equals mhead, save equals mhead.value, delete old, return value, etc. something like this. So this is generally the way to do it, right? Because if you think about it, what you're going to have to do is you're going to have to get rid of the thing that's at the head, and the problem is that if you get rid of the thing that's at the head, then the whole linked list will die, unless, of course, what you do is you move the head pointer forward and then you delete the old one. And so in order to delete the old one, you have to actually remember the original head value. And then here, you're about to delete the thing before you return, so you have to save the value. So it's kind of annoying, right? It's like, I need to remember the pointer so I can delete the pointer. I have to save the value so I can return the value. But then here I just delete the old thing, so then both this and this go away, but then I still have the two values, right? Old is still pointing to the old enum head, and save is still the value. Oh, I guess I should have called it save, not value. There we go. Alright, so that's basically how to do it with a singly linked list. And maybe we'll talk, let's do it with an array now. So how do we do this with an array? So with an array, what we do is basically, let's draw a set of boxes. So here's my little, let's try to draw some lines that are even. Or maybe I can even, you know what I can do? I can just draw a box, and then I can copy paste this box like this. And then, okay, so let's do it like that. So let's say that we enqueue some stuff. So let's enqueue 2. Well, okay, so let's enqueue, right, 2, 3, 4, 5, 6, 7, in that order, right? So what we know is that this thing here is the current and then we know that this other thing here, oops, so this is the current of the line. And so this is getting into how the project is actually done. So if you look at the project, what you'll see is that there's actually, this is exactly what it's doing. So let's look at it here. You notice that there's a start and an end, and I'll explain how all this is working. So basically, as you enqueue, right? As you enqueue, you stick a new thing. So if we want to stick a new thing on, we would move the current back, and we would insert, say, 9. I'm skipping 8. 8 doesn't exist. And then let's say that I want to dequeue a few times. So I enqueued 9, and then I'm going to dequeue 3 times. And so what's going to happen is, the first time it's going to return, and then it's going to basically erase 2, and then it's going to return, then it's going to move up to 3, and then it's going to erase 3, and then it's going to move up to 4, and it's going to erase 4. Now this one, so this one returned 2, this one returned 3, this one returned 4, right? So that's how they worked, but it doesn't really matter, at least for this, right? So the point is that, there we go, it looks a little bit better. So, okay, so now what do we do, right? So now let's say that we enqueue a bunch of stuff. So let's say we enqueue 17, enqueue 3 again, enqueue 12, enqueue 8. And so let's enqueue a bunch of stuff. So what we do is we keep inserting at the back. So then what do we do? We say 17 here, 3 here, 12 here, and then we reach the end of the array, but the good news is that the current front isn't here, so we can go back here and go 8. So now what we do is we will move the current back all the way here. So actually now the current back is in front of the current front in the array. So the only problem here is what happens, so this is where the project comes in, is what happens when current back hits current front, right? So that's one of the questions that happens. And the other question is, okay, well, how do you know, so that's how you know if there's a stack overflow, is basically if the current back gets up and hits the current front. So if you try to enqueue, say, 10 again, and say you enqueue 10, enqueue 15, and then you try to enqueue 20, so 10, 15, and then 20 would go in here, but the problem is there's already something in here. So that's what we call a stack overflow again, right? So basically when the back hits the front, there's a stack overflow. And so that's a problem, right? But what you're going to do in your project is you're actually going to fix this. And I'll tell you how you're going to do it in just a minute. But yeah, so this is how you would do it as an array. So as a linked list, you basically do it almost the same way as you do a stack. You basically, it's sort of backwards, where the front of the line is the M head, the tail is the back end. The only difference between this and the standard linked list that we talked about is you do need to keep track of the tail node. So you do need to keep track of the tail node. Okay, so let's talk about the project for a second. So now we talk about the project. So basically the queue in the project is a queue of queues, or it's a linked list of queues, right? So I don't know if I told you this already, but the this class, the current course chair really loves turducken projects. And so you can see here that this is a list of queues which are dynamic arrays. So basically, so it's like two different data structures kind of mushed together. He just loves these things. I don't know why, but he does. So fair enough. Okay. So so basically the reason why I tell you that they're always turduckens is because you really have to implement these two things separately. So the first thing that you should try to get working is your your queue functionality with the start and the end business, right? So you see here, it's exactly the kind of drawings that I was doing here, except now there's two. So you might be like, what the heck? But I'll explain what's going on here in just a second. So basically here's a queue, 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 here's a queue. They're all arrays. All right, and so now, what happens when we fill up one of these arrays? So the standard thing would be to copy the array and double the size and do that, but that's an O of n operation. So he's actually telling us something good in this case, where because it's an O of n operation to copy an entire array, often you will try to avoid that. And so how are we going to avoid copying the entire array? Well, the answer is, what we're going to do is, let's say that let's steal our queue here, and let's put in our start and end. Default to 50 now. I really want it to default to not 50. I keep hitting 25 and it keeps going back. Okay. Okay, so now here's the start and here's the end. And so that what you're going to do now, let's say that we do enqueue some more stuff. So let's say we enqueue 10, and of course it went back. And let's say that we enqueue 15, like this. Okay, so basically now here's the start, here's the end. We see that the end is equal to start minus 1, or technically there's other conditions where start could be here or end can be here. It really doesn't matter where you put the start and the end, as long as either end plus 1 is equal to start, or end, I guess it's really end plus 1 mod length is equal to start, right? Something like that. So you'll have to think about that condition, right? So it's either going to be end here and start here. It can't be end and start like this, right? No, because the end has to come before the start. But it can be like this, right? End and start always have to be touching like this. Okay, so, it doesn't really matter where you put the end and the start. The only difference is that it just determines which order things are going to get popped. So, okay. Or I guess dequeued is the real way to say it. So, okay. Now, let's say that we have this, and then we hit the end, right? Where this is full now. So what we're going to do is we're going to create a double-sized thing, a new array that's double the original size. And then what we're going to do is we are going to put them in a linked list. So now this is in a node. Right? So this is in a node, and then this is in a second node. And then here's the next pointer. So now what you get is you get something where the start is right here. And I guess it really doesn't matter where the end is yet because nothing's in there. But then you insert stuff in. And 1, 2, 3. So queues can have duplicates. It doesn't really matter, right? But anyway, so here, and now we have start and we have end. Like this. So here's the start and here's the end. Now what happens if I dequeue right? So if I dequeue now, what happens? So if we dequeue, the thing is that we have to remember that what's going to happen is that the first person or the first number to get stuck in our queue was 6, right? So what's going to happen is we're going to pop out 6, right? And then we're going to advance the start. And then if we dequeue again, right? We're going to get 7. Let's just copy paste that. So what happens if we dequeue again? We're going to get 7. And then what happens if we dequeue again? We're going to get how do I escape? Okay, we get 9. Okay, I'm just going to delete them. And then we get 17. My God. Okay. Click on it, and then I try to drag it, and then it picks up the box. Okay. So, okay. DQ again, we get 3. DQ again, we get 12. DQ again, we get 8. DQ again, we get 10. DQ again, we get 15. And I don't know if they're exactly matching, and it doesn't matter. And then we DQ again, and we get 5. Come on. There we go. Okay, and now what we have is we have that start and end are basically at the same place, or maybe it's like this, or whatever. But the point is that finally, the first array is now empty, right? So the first array is now empty. We never insert anything. Once you start the second array, you never insert into the first array again, right? So what that does is it guarantees that after a finite number of DQs, the first node will have an empty array, right? And so that's good, because now what we can do is we basically delete this node, right? So we delete this node, and then once we delete the node, this is now the new head. And it's always possible that if this node gets filled up, we need to have another node and another node and another node. So that's exactly what we do. So basically, let's do a really simplified example where you start off your queue with maybe one node inside the queue. So here's an example with one node in the queue. And then here, your next node will have 2 blocks in the queue array. And then here, your next block will have 4 blocks in the queue array. Of course, now it's going a little bit past the end of the thing. That's just fine. And then the next one is going to have 8. So we need to make this a little bit larger. And so on the project, there's a minimum size that you start with. This will be m min size or whatever. That's the thing that he specified there. Yeah, so the second one is always 2 times the size of the first one. Okay, so basically this is how the linked list is going to go. Something that has 1 that goes to 2, and basically just pretend like this is a certain size. This is double that size. This is quadruple that size, and then finally this one's going down here, right? So this is your linked list. Now, if all of these are full, then you would create another one, create another one, create another one until you hit the max size. And then you have to do something else. But I don't want to discuss that because I didn't read it very carefully. I know it says you go back to the minimum size or something, but there's some, it seems weird to me. There's some weirdness that, anyway, there's some weirdness that happens at the maximum, so be careful. It says like go back to the minimum size rather than the maximum size, or something doesn't seem right about it, but maybe it's what he intended. Every time I've thought that like he can't possibly mean something, he means that. He actually means it. So I'm not going to second guess him. I'm just going to assume that he means what he says, and that it's correct. But it doesn't make a lot of sense to me, so that's why I want to look at it more carefully. Okay, so this is basically it, and then that's really how it works. And so basically, you always DQ from the smallest one, you NQ into the biggest one, and then once they're the same one, then you start moving start and end around. Here, only start's going to move until it gets to here, then start's going to move until it hits end, and then start's going to move until it hits end, and then finally start's going to move until it hits end, but then the queue is just empty. Or you've inserted new things into here, and hopefully this one isn't full. So that's how it works. So my hint for this type of project, so if I have to tell you the hints for this type of project, is do the queue first, test it out, make sure it all works, then do the linked list, test that out, make sure that works, etc., etc. Then put them together. Okay? So basically we have 3 weeks for each project now. So the good news for you is that you have 3 objectives and 3 weeks. Okay? I think that you could do a very easy pace, very slow, non-stressful implementation if you do one of these things. And I might even start like forcing you guys to do that, because I've noticed that, here's the thing, I've noticed that everybody who doesn't finish CMSC 341 projects, the issue is that you don't start early enough. And I know that a lot of you will remember from 201 and 202 that you've got to start early on projects, that you cannot let this stuff go. But it happens. So I'm going to try to kind of find a way to unobtrusively, I don't want to annoy you people with extra requirements, but I do want you to start. And I want you to see if you can get the queue banged out in the first week of this project. And the reason why is if you get the queue banged out in the first week of the project, and you've tested it out and you know it works pretty well, and then you bang out the linked list in the second part, and then all you have to do for the third week is basically stick them together in the turducken merging and make sure they all work, then you are really gonna, it's gonna be like 3 to 4 hours a week on the project, rather than being 10 to 15 to 20 hours all at once. And so that's my big hint on the project stuff. And I'll go over more of the project when I actually implement it, which might be tonight. Because actually, so it's a turducken, and I don't like the turduckens from last semester, but this one I actually kind of like. I do like this project. I think that it is 2 data structures, but it actually makes sense. It's something that you might do real world, right? So it's not something like certain project last semester. There was a lot of stuff where I looked at it and I thought to myself, like, no one would ever do this, But okay, so let's talk about the last data structure, which are Deques. So basically a deck is it's a stack queue mushed together. Okay, so it has 2 operations. It has basically you can either call them NQ or push, so you can call them NQ front, or you can call it push front. There's NQ back or push back, and then there is NQ DQ front or pop front, and then there's DQ back or pop back. So I don't care whether you use the stack or the queue language to talk about it, but basically the point is that you have a linked list like this, and basically what you're allowed to do now in a deck is you are allowed to put stuff on the back. You can stick something on the back, and then you can also stick something on the front. So you can do this. You can also do this, right? And you can also remove from the back and the front. So this operation here, right? This and this are the enqueuing operations. So this is like an NQ back. This would be like an NQ front. And then if you removed it, right, so if you have this data structure and then you delete them, this would be the DQ back, where we delete this darker blue node, and then DQ front, which is something where we delete the front node. So the thing about this thing is that this is definitely something you don't see as much. And the reason is it's more just like a linked list. And so oftentimes, so I think the preferred implementation is as a doubly linked list, right? And the reason why you need it to be a doubly linked list is because you can't play the same tricks as you played with the stacks and the queues linked lists. And you can try to do this, but I don't think you're going to be able to succeed. The reason is because in the stacks and the queues, you only ever added to one side and deleted from one side. And so we could always kind of maintain control of the vast majority of the data structure. But here, you're always going to be possible to NQ and DQ at the head, which is the easy way thing, right? So this is easy to put a new element, a new head in, right? Easy to delete the old head. But the thing that's hard is if you only have a singly linked list, it's hard to delete the last element. And the reason why it's hard to delete the last element is because if you have a pointer to the last element, then the issue is that you can't actually, you need this element as well, right? You always need this element. And the reason why is because if you don't have this element, then as soon as you delete this one, right, this pointer still remembers the blue ghost. But this one here is pointing out into nowhere. So that sounds either like a segmentation fault or accessing corrupted, really more like data, right? Because technically that data could be reallocated and overwritten. So we don't want this pointer to still be pointing off into the abyss. So we have to change it to null. But the only way to change it to null is to have access to this data element right here. And so in order to get access to this data element, the general way to do this is to have a back pointer, where you can just say, okay, we can go back by one, and then we can go forward. And so we go back, we go forward, we set the previous dot next equal to null, and then we can delete the last element. So that's kind of the idea here. That's why you would want to do this. Yeah. Okay, so that's basically how Deques work, and I think, oh my god, so this streaming stuff is really bad. I might try to do it through Discord next time. Maybe we'll try that on Thursday to see if it's any better, and then I will also, because there's only 20 of us here, so I think that maxes out the stream limit at about 20, and then I'll just release the lecture pre-recorded. So, okay. So Deques, stacks, and queues. That's what to think about today. And Project 1. So Project 1 is nicely divided into 3 parts. The gimmick here is that this thing is a circularly linked list. So it's actually linked back like this. But here's the thing. Remember when we talked about circularly linked lists, like it's not really gonna change anything for you. Except for the fact that instead of inserting at the end, you have to insert where the head is the next node, right? So if this thing is pointing to head, then you have to insert this node in between the head and this node, right? That's how you get the circular structure. And also, in a circularly linked list, the one important thing about a circularly linked list to remember is that when you have a circularly linked list with one node, the node basically points back onto itself. Right? So that is how the next pointer works for a circularly linked list. Or I guess I really should just do like the circle thing. And then here, right? So basically this is how the thing works. So the next node comes out and it goes back in, right? So it's pointing directly back into itself. when you have one node. The only time where this doesn't happen is where a circular linked list is empty. So a circular list with one node points back to itself. The only thing that is the exception is a circular list with no nodes. I might be doing that. Yeah, I can do that. Is just empty, null. Okay, so I think that's all for today. I think we've done stacks, queues, and Deques. Let's make this into a big PDF. So I can delete most of the complaining here, I think, because that's pretty pointless. And then we're going to talk about stacks, queues, and Deques. Let's move this stuff to here. Maybe next time I'll do a bit of implementation of stacks, queues, and Deques, so that'll be fun. I know I implemented a stack already, but we can implement the queue and the deck. So, you know, that will also be fun. So let's make this. I know that this is going to be a horrible PDF to actually look at, but let's make it into a PDF, and then I'll post it. There we go. Okay. Yeah, I'll probably be posting them on the Discord first, and then maybe on Blackboard. But anyway, I'm sorry about today. I don't know how bad the buffering was. I don't know how bad anything was. I'm sure this was a mega frustrating lecture. It's been extremely frustrating for me as well. So I'm going to try to get this resolved by next. That maybe I'll do the Thursday lecture. I know that this was pretty rough, but I'll try to get the next lecture done. I might even just post it as just a YouTube video, and then when we can go back to live lectures again, we'll do that. I apologize, but that's it. Okay. Yep, let's save the thing as a PDF, and then let's call it a day. All right, thanks everyone. I'll be around if you need any Project Zero help. Just send me a message, and I'll help you out with Project Zero. And then we'll start working on Project 1, right? Start working on Project 1 today. Today. All right. I'll talk to you guys later. Thanks, everyone.